Okay, hello everyone. So this is Chem. I'm going to be going over some Debye-Huckel's and Davies equation, and then if I have time, go into voltaic cells and some of that chapter. So whenever you're doing the Debye-Huckel's or Davies iterations, you usually want to start with one, right? Your KSP. In terms of molarity, for each ion. After you've written your KSP, you can probably, for that first time, you can assume it's ideal. So, gamma plus minus equals to 1. After that, you can calculate molarities for each ion. I put molarity, because I'm used to molarity. After that, you calculate the ionic strength. And then you recalculate. I have 1, 5. I skipped 3. Gamma. You can recalculate using either the Davies equation, which I believe that's the longer one, or you can recalculate using the Debye-Huckel. So I'll just write both. Debye-Huckel. After that, you basically just repeat. That's what makes it a reiteration. So you're going to use your new, I'm pretty sure that's called gamma. I'm sorry about the birds if you can hear them. I'm outside. Anyway, you're using your gamma in the KSP. Continue steps. Okay, and then from there you just can go back to the top, rewrite the KSP using the new gamma, and you calculate the molarities, calculate ionic strength, recalculate the gamma, continue and continue until the gamma is the same. Granted, it's probably never going to be exactly the same, but if I remember correctly, by the same we normally meant to 5 decimal points. So like the first 5 numbers should be pretty much the same. Cool. I'm gonna write in some of these. So the ionic strength equation is, let me put that in a different color, equals m over 2 sum of, or sigma, v for the positive and z squared for the positive. That's one version. We'll probably use that in different areas, but the one version that we're probably going to use is this one, actually. Let me make this a bit thicker. M of positive times z squared. And then molality of negative and the charge negative. And then let's see, KSP is like this. KSP is equal to gamma plus or minus V positive plus V negative M positive to the power of V positive times M negative to the power of V negative. And then the Debye-Huckel is, I'll put that one up here. Log gamma plus minus to negative 0.5092 to the absolute value of z charge positive and charge negative. It's absolute value. Times the square root of the ionic strength. The Davies is a bit bigger. It's still the log minus negative 0.51, I believe, 2. Oh no, to the absolute value of z positive, z negative. You know, let me see if I can move. And then let me make that a bit bigger. To the I over m naught. 1/2 is just another way of doing square root. That's how she usually writes it, I think. So that's how I write it. Minus 0.30 m naught. Okay. And then note that m naught is 1 molar. Cool. So let's do an example of this. We have KSP for MnOH2 so that's our ion, and they give us KSP as 1. I should probably be writing this in black so we know that it's for set. (1.9 times 10 to the negative 13). Pretty small. And then we're asked to find solubility. Let me rewrite this one too. H2. And then at 25 degrees Celsius. I don't think we really need to know the temperature. It's just nice to know that, okay, we're keeping the temperature constant, because you have to acknowledge that solubility will change depending on the temperature of the solution. Okay. So then from there, we write out our KSP. So KSP is equal to gamma plus minus the power of V plus V negative times M plus and M negative V negative. I might want to move that down. Is this a selection? Move that down a little bit. Okay. First off, we need to look at this Mn. We have Mn and OH too, which means that there are twice as many OHs as there are Mns. So it's going to be Mn is equal to 1/2 OH. And I know this kind of seems counterintuitive. It kind of feels like it should be 2Mn is equal to 1 OH, which you could probably do that as well. Because then this will just come over here, right? The way I used to think about this is it takes so many OHs for the Mns. It's not exactly stoichiometry, because it's not 2 OH to 1 Mn. It takes this amount of OH for that amount of Mn. Yeah, I never came up with a good mnemonic. I was just remembering there are twice as many OH as Mn, so that means that I need to do 1/2 for the OH. Or if there's 3 times as many, I have to do 1/3, which kind of make them equal. I think this was one of the things she corrected me on, so yeah. I know that ratio is right because that's what she wrote down on my little desk, so. Anyway, from there we can also do the V's because we have the charges, right? So we have Mn and OH. OH we know is a -1, and if there's 2 of them, then that means that Mn must be +2, right? Because for this to be a negative, this one needs to be 2 positive because there's 2 OHs, so that means there's 2 negative charges for that. Cool? So we can write those in as our do we need those just yet? Oh, we don't need the ionic strength. Oh well, they're good to have anyway. So COH equal to -1. ZMN is equal to +2. What we need for the V's is just the amounts. So VOH. So there's 2 OHs, so it should be 2. So the V is closer to the stoichiometry. No, I want to go down. Okay. And then because this is our first iteration, you assume it's ideal. So we assume that's 1. You can write in the V plus and the V minus, so that's going to be 2. No, the 1, the positive. Yeah, positive is 1. I am missing a little plus sign in here. Oh no, it's up there though. I just didn't write it down here. All that times Mn is positive, so molality of Mn to the power of Vmn, which should be 1, times molality of OH to the power of the V, which is going to be 2, I believe. Yes. Cool. So that should condense. Oh, wait, we need to plug this in. So because we have this equation up here, we can plug in for Mn or OH. I would probably plug in for Mn, just because I don't like dealing with the squared up there. So we can go N is equal to 1/2 of OH. Just because I don't want to deal with the squared there. So then that equals to 1 to the power of 3, because 1 plus 2, times 1/2 MOH. H power of 1 times H power of 2 and that should give you, let me put it over here. This is just going to become 1, so I'm not going to write it anymore. 1/2. It's going to be 1/2 times 1 MOH power of 3. Right? No. I think it'll be to the power of 2. Yeah, no, it's going to be product of 3 because these two are going to be multiplying each other, so you can add. Exponent rules. We could also plug in our KSP, which is given up here. I just haven't been writing it. 9 times 10 to the negative 13. Now that we have this. Oh. So then from there we can move the 1/2 over, and later the 3 squared will move the 1/2 for now. So it can be 2 times 1.9 times 10 to the negative 13 equals MOH cubed. And then you can do the cubed root to get rid of that cubed, which I believe that is, I'm gonna need to plug it into my calculator in a second. So far that's giving me the cubed root of 3.8 times 10 to the negative 13. Recall that you can also write cubed roots like this, like 3.8 times 10 to the negative 13 to the power of 1/3. Sometimes that's easier to put into your calculator. Which that gave me 7.24 times 10 to the negative 5. Don't believe KSP has any units. So these must be units of molality. And then from there we can use that Mn is equal to 1/2 OH. Oh, I probably should have written that like this. MOH. Such that from there Mn is equal to 1/2 7.24 times 10 to the negative 5, which that should be 3.62 times 10 to the negative 5. And then I believe molality is moles per kilogram. I always tend to mix it up with molarity, which is moles per liter. But I think this one's by weight, so moles per kilogram. Cool. So then, now that we have, I write that in a different color. MOH and Mn. We can go on and calculate the ionic strength. So ionic strength is equal to 1/2, that is a bad 2, sum of Mn. If you want the general equation, it's up here. Mi zi squared, m negative I z negative I squared, and then m/2. Did m/2? I usually just do 1 over 2. Oh, that's for the other version. There's a version that uses the z's too. That's why I usually use 1 over 2. The v's, I mean, my bad. MNI. So that's positive, which means we also need to do the positive z squared plus MOH ZOH squared so then we should be able to calculate that using what we just found in the previous KSP equation. So it's going to be 1/2 MN we found to be 3.62 times 10 to -5 mole per kilogram. And then the Z we found up here with the charges, right? Because the Mn is positively charged and the OH is negatively charged, you have 2 negative OHs, and you know those are -1. Sorry about the noise. And then the Mn is 2 positive because you need the negative. It needs to equal to 0. So if you have 2 -1s, you need a +2. And then that's going to be times ZMN +2 squared plus MOH, which we found to be 7.24 times 10 to the -5 moles per kilogram. And then ZOH, which is -1 squared. And then this one's pretty easy. You don't really need to rearrange. You just plug them in as is. So we'll do 2 sigma. Oh yeah, no, turn back on. Okay. Space to that 1 times 4 plus 1.24 times like this. I wish we could use like the graphing calculators, where you can like go up and grab the previous numbers, but I'm with my scientific right now, so -5. That gave me 2.1726-ish units moles per kilogram, which then got turned into divided by 2, 1.086 times 10 to the -4 as our I. Cool. And then now that we have our I, we can do either the Debye-Huckel or the Davies equation, right? So I'm going to go ahead and do both. So I'll start with the Debye-Huckel because it's a little bit shorter. So again, that's this one up here. I wonder if I can just copy and paste. I'll rewrite it. So sorry if I spelled the name wrong. Names are not my forte. So then the Debye-Huckel equation is log of gamma plus minus is equal to -0.5092. absolute value of C plus, C negative, and then square root of I. Cool. So then to plug that in, I like to start with just moving the log over. So we add a 10 to the power of to both sides, because that kind of gets rid of the log there. So then that isolates for gamma plus minus is equal to 10 to the power of negative 0.5092 absolute value. The Z plus is going to be for your Mn, which I believe is equal to positive 2. And then this is going to be your OH, which is equal to negative 1. And I believe you're just multiplying those together. So, I'm sorry about the parakeets. And then your I is what we just solved for right there. And you could plug that all in, but I'm probably just going to do up until we do the 10 to the power of, just so people can alright. Negative 0.5092 times square root of 1.086 e to the negative 4. That got me negative 1.061 times 10 to the negative 2. I usually just drop the units. I don't know if she expects you to keep them, because with the square roots and the 10 to the power of it all, it's going to end up wonky anyway. And then this one is really unit driven. It's more of a value. Anyway, 10 to the power of answer 9.758. I guess it should be 9 when you do rounding. Times 10 to the power of negative 1. Oh, I can... negative 1. Which that's basically 0.9759. And then from there, if you were going to do a second iteration... No, I want to scroll. If you were to do a second iteration, then you would go back to KSP is equal to, I guess I can plug that in already. You know what, let me just go up and copy it. Sorry, y'all. There we go. Clean that up here. So then we would have our KSP being 9 times 10 to the negative 13 is equal to our now new gamma, which is 0.9759 V plus and V minus. It's the exact same thing we did up here with the 1 plus 2. 1 plus 2. Could actually probably, I think I've just started from some of these already. Oh no, because you would need that. Oh well. I guess I'll write it all out. M plus N times 1 to the power of 1, my bad. MOH to the power of 2. You can again plug in the MN. Half MOH, etc. to strength. And then you go and you calculate this one again, and then you go back and you plug it back into your SP. So that would be your second iteration if you were to do one. It takes a while though, so I don't really want to. I guess I will do the version over here. One. No, this one. And you can also do it with the Davies equation. So the Davies equation is log y, not a y, gamma plus minus is equal to negative 0.51 absolute value of z positive times z negative, all that times I, all that times I over MO. She has it as 1 over 2. It's basically the same thing as square root. I'm going to keep it as 1 over 2 because it's less straight lines to write. And that minus 0.30 I over M naught. I'm just get rid of the 0 for now. No, that's not cool. I can just scooch this over. Zero. Cool. Don't forget that M naught. Let me write that in a different color. I believe molality is also written like that, with the little M looking. You could start by doing 10 to the power of, it's kind of already a big equation though, so I think I'm just going to jump right in. So log gamma plus minus is equal to negative 0.51 to the power of z positive, which remember we have our charges the same as the ones we used over here, so it's going to be positive 2 times negative 1. Just a reminder that these mean absolute value. So like if it says positive 2 times negative 1 absolute value, that's going to give you negative 2 inside, but then when you do the absolute value it turns positive, so it's going to be equal to 2. Just a reminder. Anyway, back to this. We have our I that we calculated over here. Let me make sure I can see it. I is equal to 1.086 times 10 to the negative 4. Molality is also so I'm going to just be writing the mu. Okay. Have 1.086 times 10 to the negative 4 mu over 1 molality. I'm going to copy that because I don't want to rewrite it 1,000 times. It's not 1,000, it's only 3, but you know what I mean. Divided by 1 plus, that needs to be to the power of 1 over 2. Here's the paste. Ugh. Plus that times that minus 0.310. No, not 1. I don't know where I got the 1 from. 0.30. I guess it's like a phone number, huh? Let's see if I can copy again. This time, just the inner part. No. And that's it all fully written out. So let's work on simplifying that. Plus minus. Negative 0.51 times 2. And then I'm going to need to plug this in. (1.086) e to the negative 9 divided by 1. And don't forget that it's squared. Square rooted of. And then it's that. Which I got 3.295 times 10 to the negative 0.5 for that. And then it's going to be that divided by 1 plus the same. So from that, I got around 3.295 times 10 to the negative 0.5. Well, I guess it's negative 5. And then that's going to be minus minus 0.3 times 1.086 10 to the negative 9 I'm gonna write it down here because I'm just plugging everything in all at once. And then times negative 0.51 times 2. I got negative 3.3612 times 10 to the negative 5. I'm going to come and put that back in. 0.3 minus 3.258 times 10 to the negative 10. Do note that for Debye-Huckels, you want to keep as many decimal points as you want. So if you noticed, I wrote this first. That's because I was plugging everything into the calculator in pieces and then just keeping my past answer and adding to it. I've just found that that increases your accuracy. But yeah, you do you. So once we have that, we can do the 10 to the power of to get rid of the log. And that gets us gamma plus minus is equal to negative 3.3612 e to the negative 5. I got 0.99. My logic's telling me that should be lower or less, close to 1, but I lost this number while I was recalculating this one. So I can try and recalculate that without moving anything out of my calculator right now. Answer divided by 1 plus the answer. And then that minus 0.3 times 1.086 e to the negative 9. Then that times negative 0.51 times 2. And that to the power of 10. Oh no, I got a similar number. Okay. We're good. So I guess I'll just erase that since it was irrelevant. Okay. And then if you were to do a second iteration, which I think on most exams she's not going to have you do a second iteration. She might have you do it on your homework. But because it takes so long, she'll probably just have you explain what you would do in a second iteration. So in a second iteration, you would go back to the KSP. We'll copy and paste. I'll probably copy more than that. Actually, I can probably copy most of that. With the only change being we found a different gamma this time. So this one comes into there, 0.99. And then, it's all the same. You go through, you calculate for your molarities. Find molarities. My bad. Find molalities, then you find the ionic strength, then you calculate gamma again, and then continue. Yeah, so that's Davies and Debye-Huckel. This first part's usually the same for both. It's just finding the different ways of finding the gamma. My brain keeps telling me that the gamma is probably the activity coefficient, but that I'm not 100% certain about that. And in my notes, it's always just gamma, so can't reliably tell you. Ionic activity parameter is the closest thing that I see in my notes. But anyway, I'm sure you know what that is, what the gamma is. It's related to solubility, and it's related to how the molecule or ions act, or compound acts in the solution. But yeah. So, just to recap, you start by writing the KSP. You use the molalities just as the symbols, like the molality of your positive ion, molality of your negative ion, and then you're going to substitute one for the other so that you only have one in the entire equation. You're going to solve for that, and then use the substitution that you used to solve for the second one. Then you're going to calculate the ionic strength using the ion's molalities, using the ionic strength equation right there. And then after you've calculated the ionic strength, you can recalculate the gamma by either the Debye-Huckels or the Davies. If you pick one, you stick with that one until you're done with all your iterations. And your iterations are just repeating by using the gamma that you calculated or recalculated into your KSB, and then recalculating molalities, recalculating ionic strength, and etc. But yeah, I hope that helped.